everyone, Katrina here, and today I'm going to show you how to simplify rational expressions and how to state restrictions. We're first going to dive into the three-step process that we can follow every time, then we'll look at some examples to clear things up. So here is our three-step process. So number one, we have to factor both the numerator and the denominator to see if we have any like factors. The second thing we do is we cancel out the like terms that are found on the numerator and the denominator. And our third step is to state any restrictions. Essentially, restrictions are anything that make the rational function go to 0 on the denominator, or they could be anything that you have canceled out. So let's take a look at that for a second. So there's two types of restrictions we have to state. So if we cancel terms, we have to state that as a restriction, and also whatever is on the denominator, we have to include that into our restriction. If we cancel something out, that means that we have a hole at that point and our function does not exist there. And if it's still on the denominator, then that means that we have a vertical asymptote at that value of x, and our function does not exist along a vertical asymptote. So either way, we still have to state that as a restriction. So one, anything that makes our denominator equal to 0, and also second, anything that we have canceled out, because these represent values of x at which the function does not exist. Let's look at an example, and this will help clear things up. So our first example is f of x equals to x squared plus 7x plus 12 divided by x plus 3. So our step one is to factor the numerator and the denominator. In my previous videos, I show many different techniques how we can factor. So here, let's apply one of them. This is a trinomial, so we can use the product sum rule over here. So we have no leading coefficient, or our leading coefficient is just 1, so we can do the fast version of this rule. So our product equals to 12, and our sum equals to 7. So what are two numbers that multiply to 12 and add to 7? 3 and 4 work. So let's factor the numerator. So now we have x plus 3 multiplied by x plus 4. Can our denominator be factored anymore? I don't think so. It's already in a factored form. So we divide our numerator by our denominator, which is x plus 3. So in this case, we're going to move on to step number 2, which is to cancel out the like terms. So here we can see that x plus 3 is in the numerator and in the denominator. So these can be canceled out, and then we are left simply with x plus 4. Okay, now let's move on to step number 3, which is state the restrictions. So remember what I said earlier is that we still have to include the terms that we've canceled out as part of our restriction. So here, let's see what that would be. So we've canceled out the term x plus 3. So to find the restriction, you set your value to 0 and solve for x, because if x equals that value, then that term will be equal to 0, and it will nullify our function. So here, if we use our algebra techniques, we see that x equals to negative 3. So that means that x cannot equal negative 3, because if it is negative 3, then it will cause the numerator and denominator to be equal to 0. Let's take this a step further, and let's see what does this actually mean in our case. So we can see that the resulting function that we get after the simplification is a linear function, because it has the format y equals to mx plus b. So here our slope equals to 1 and our y-intercept equals to 4. So let's try drawing that out to see what we actually get. So if we graph this very roughly, we have our y-intercept of 4 and a slope of 1. So we have some graph that looks like this, linear function. However, we saw that the function cannot be equal to -3. So if we zoom in, let's redraw our function to see what that means. So that means when x equals to -3, our function simply has a hole. So it just does not exist at that point, which is quite funny. So essentially a hole is just a removable discontinuity. So at that point, sorry, I'm trying to draw a linear function there for us. So at this point, x equals to -3, the function is undefined, it does not exist, there is a hole. And that is why we have to include this restriction in our simplification of the rational function. So that should give you a bit of a visualization so you understand the deeper meaning of what it means when you cancel out like terms in a rational function. Okay, we're going to move on to another example that will allow us to see both holes and vertical asymptotes. So we have f of x equals to x squared minus 4 multiplied by x squared plus 9x plus 18. So this first term here is divided by x plus 6 all squared, and our second term here is divided by 2 multiplied by 2 minus x. So this is a bit more of a complicated problem, but we're still going to apply the 3 steps that we learned previously. Okay, so the first step is factor. So we always have to start with factoring. Up here, we can see that we have a difference of square. You learn how to factor difference of squares in my previous video. So difference of squares factor as x plus 4 multiplied by x minus 4. And our denominator over here, well, this cannot be factored any further. So let's see what else we can do. So let's try factoring our second term, this one over here. So this again is a trinomial. So that means that we are going to use the product sum rule in order to factor this. So what are two numbers that multiply to 18 and add to 9? Well, 3 and 6 work. So let's factor that. That means that we have x plus 3 multiplied by x plus 6 all over 2 times 2 minus x. Oh, I realized I made a mistake over here. This should be x plus 2 and x minus 2 because 2 is the square root of 4. Okay. So now we have this factored. The other thing I want to look at is I don't like having a negative in front of my x. I usually like having my x with a leading coefficient of +1. So that means I want to factor out a negative right over here. So let's rewrite this. So we've got x plus 2, x minus 2 over x plus 6 all squared, and then multiplied by x plus 3 times x plus 6 over, we're going to take out the negative, so we have -2 and then x minus 2. Okay, and you can see that this was very helpful because now as we move on to step number 2, which is to cancel like terms, we have like terms that we can actually cancel out. So let's take a peek at that. So we have x minus 2 on the numerator here and x minus 2 on the denominator. We're able to do this cross cancellation because our terms are separated by a multiplication. So that means this is valid mathematically. Secondly, we can also see that we have an x plus 6 over here and an x plus 6 over here. So we can just cancel out one of them one of them from the numerator and the whole one from the denominator over there. So now let's write out our simplified version. So we've got x plus 2 multiplied by x plus 3 divided by negative 2x plus 6. So this is already so much more simplified than what we started with. But now we have to remember what we've canceled out, because we have to state our restrictions as part of our step number 3. So we have to get the restrictions, both of what we've canceled out. So we've canceled out an x minus 2, and we've also canceled out an x plus 6. So let's look at those restrictions first. So if we have the x minus 2, so we've got x minus 2, we have to set that equal to 0 to find our restriction. So that means that x equals to 2. Therefore, our restriction is x cannot equal to 2. And then our second one is x plus 6 equals to 0. So if we rearrange that equation, we have x equals to negative 6. Therefore, our restriction is x cannot equal to negative 6. So what does this mean in terms of our graph? So both of these were canceled out. So that means that these two terms over here are wholes. So just like we saw in our first discontinuity, it's simply a point that has been removed from our function. It is a point at which the function does not exist. Okay, so now let's look at our second restriction. So that is whatever we have left on our denominator. So here we see that left on our denominator, we have x plus 6. So that means that in this case, if we set this equal to 0, we have that x equals to negative 6, so that x cannot equal to 6. But wait a second, we thought that was a whole. But in this case, we actually had two factors of negative 6. So we canceled out one, but we still have another. Since we have a remaining x plus 6 on the denominator, that means that x equals to 6 is the equation for the vertical asymptote, and it's actually not a whole. So that is a little bit tricky. So whatever we have left on the bottom becomes our vertical asymptote. So let's do a little summary of that. So our restrictions then are x cannot equal to 2, and we said that is a whole. And then x cannot equal to 6, that is going to be the equation of our vertical asymptote at x equals to 6. So a vertical asymptote is a line in which the function does not exist. So if the function does not exist there, then you cannot have any of your values equaling to that point. So it's a similar concept between wholes and vertical asymptotes in the sense that it's a point or line at which the function doesn't exist. A whole in particular is one point. So it's just a point of the function, where a vertical asymptote is a whole line in which the function does not exist. So today we learned the 3 steps how to simplify a rational expression and how to find the restrictions. We learned that there are 2 types of restrictions that we could have. We could have a whole, or we could have a vertical asymptote. So whether we cancel out terms or if we still have terms left on the denominator, we have to include those in our final restrictions that we have stated right over here. So if you enjoy this video, please give it a like and comment any questions that you have, and subscribe for more fun and easy to follow math videos. I'll see you next time.